Hello, my name is Jakub Jedek, and I will be presenting joint work with Jakob Holm. So this is a presentation about algorithms for planar graphs. So obviously this is something that has been very well studied, but in the previous work, it has been ignored that we may have an embedding, and maybe this could be somehow useful for our computation. And our goal in this paper is that we want to get improved algorithms by exactly using the fact that perhaps we have an embedding of the planar graph. Because I mean, in practice, in like actual applications, if we have a planar graph, well, why do we think that it is planar? Well, presumably at some point, somebody has drawn the graph in the plane, and that's why we think it is planar. And then unless we have somehow lost the embedding, then we still have it and we should be able to use it in our computation. However, it is possible to compute very nice embeddings of planar graphs in linear time, which means that if we focus on the standard sort of classical superlinear time sequential algorithm setting, then we cannot get any additional power from this assumption, right? Because whenever we have an algorithm that uses embeddings, well, we can first compute the embedding in linear time and then use the algorithm with the computed embedding. So instead, we focus on other settings, and we show that this is very far from the case for sublinear time algorithms and massively parallel computation, and that you can get improved algorithms in these settings. Throughout this talk, I will be assuming that we have a straight line embedding, but we also have results in our paper for non-straight line embeddings. Then the complexities of the algorithms are parameterized by the average total absolute curvature of over all edges, and this concept that it basically generalizes. It captures how curvy the curves are, and essentially what it says is that if the curves are not too curvy, if they are pretty straight, then maybe we don't care. So this is something that we also do in the paper, and we also show something for graphs which are not planar, and we have an embedding which is not planar, but maybe the embedding does not have too many crossings, and then we can also do something. So our results, we show how to approximate additive Lipschitz functions in sublinear time. So this is a big class of parameters, graph parameters, which includes, for example, the minimum vertex cover or the maximum matching. And we need this complexity. While previously it was only known how to do this with bounded degrees. So if you have constant maximum degree, then you can get polynomial in epsilon. But our algorithm also works if you have general degrees. And moreover, the exponent here, it is in the tens of thousands, whereas for us here, the exponent is 2.5. We also solved the following problems in the MPC setting, where we need n to the 2/3 plus epsilon space per machine and constant number of rounds. So these 5 problems we show in the paper how to solve them, but since writing the paper, we have also found some more problems that this applies to. And it's interesting that some of these problems cannot be solved in this complexity. Namely, if you had a complexity, space complexity n to the 0.99, say, then you would need logarithmic number of rounds. But for us, it is sufficient to get constant. And without the embedding, this would not be possible under the 1 versus 2 cycles conjecture, which is quite a popular conjecture in the MPC world, where it is often used to get lower bounds. We also managed to get better MPC algorithms for the Euclidean minimum spanning tree. Now, note that while the other problems that we are considering, they have some assumption, namely the assumption of having the embeddings, which has not been considered before. So in a way, we are solving different problems that what people considered. But this is not the case here. We actually get a strict improvement in the complexity for Euclidean MST in the MPC setting. This follows from our algorithm for minimum spanning tree. So what you can do is that you use a known algorithm for computing the del net triangulation of the input set of the point set, and then on the del net triangulation you can compute the MST using our algorithm that we get in our paper. And this just putting those two things together give you a better MPC algorithm for Euclidean MST. In the rest of this presentation, I will be focusing on counting connected components in MPC. So before I can show you this result, I need to give some preliminaries for R divisions. So what is an R division? R division is a tool for designing algorithms for planar graphs. And it is very commonly used. So usually algorithms for planar graphs, the way they start is that you find some variant of R division, maybe something slightly stronger than R division, but very often just R division is enough. And then you have this division and you somehow use it in your computation. And that is exactly what we are going to do also in our paper. So R division says that for some parameter R, it is possible to, for a planar graph, it is possible to divide the vertices into some regions. Note that these regions do not have to be disjoint, so it's not a partition. So we divide it into n over r regions of size order of r. So that says that basically that the regions are as small as they could be given the number of the regions. But then we say that each region shares only square root r vertices with other regions. So as I said, the regions do not have to be disjoint, and actually they would usually not be disjoint, but each region can only share very few of its edges with other, very few of its vertices with other regions, namely square root r. And then we require that edges go only within regions and not between different regions. So for example, if this is the graph and the division into regions, then this edge would be allowed, but this edge would not, because it goes between two different regions. Of course, what is allowed is that you can have vertex, which is multiple different regions. And then, of course, from that edge, from that vertex, you can have edges going to all the regions that it is in. And these vertices we will be calling the boundary vertices, the ones that are shared between multiple regions. So now I will give a weaker version of R division. So the difference is highlighted in red. And we also say that something about the time complexity that we need to compute it. So apart from parameter R, we also get parameter S. And now I'm claiming that we can find it in time n log n over S. So note that this is sublinear actually for S being not too small. And then in the rest, the guarantees are slightly worse. So instead of n over R, we get n log n over R regions. We still have the same bounds on the size. But then each region is allowed to share, instead of square root R, it is square root S times R vertices with other regions. And also, before we said that edges are not allowed to go between different regions. So now we are instead saying that for each region, there can be at most square root of SR such edges. So in a way, we have extended the definition of boundary to also include these edges that go between different regions. And then we are still requiring, we are requiring that the size of the boundary is square root of S times R. And what is interesting about this result is that we get an oracle that for a vertex, it returns the number, the regions that it is in. So this would not be interesting because, I mean, obviously, if you have less than linear time, then you cannot explicitly compute the R division. But what is interesting about this oracle is that it only uses the coordinates of the vertices. So it does not need to perform any queries on the original graph. It only looks at the vertex that you asked about. It looks at the coordinates of the vertex, and then it somehow looks where in the plane the vertex is, and based on that, it will give you the set of regions that it belongs to. So now I will give a sketch of proof of this theorem. Namely, I will give an algorithm that can compute such weak R division. So first, I'll sort of sketch the algorithm. I will show an illustration. So here we have the input graph. This is our input graph. Then we sample some edges and vertices, appropriate number of edges and vertices. In this illustration, I will be only showing what's happening for edges, but essentially the same thing would be happening for vertices. Essentially treating a vertex from a geometric point of view as an edge of length 0. So then you divide it into something that we call sectors. So sectors are just parts of the plane that are polygons. So what you do is that you take the sampled edges and vertices and you compute the trapezoid decomposition of them. I will not be defining exactly what trapezoid decomposition is. It will not be important in this talk. So it is important to remember these are called sectors, and sectors are part of the plane, whereas before I was talking about regions, and regions are some subset of vertex. So region is in a graph, whereas sector is some part of the plane. So then we compute what we call the sector graph. So vertices in this graph are well, there is one vertex corresponding to each sector, and then there is an edge between them if they are adjacent in some sense of being adjacent. So we define what it exactly means to be adjacent, and there is some very subtle point, but this I will not get into because it's not important for the intuition. So essentially what this means is that the sector graph is essentially a dual of the trapezoid decomposition, except that not quite, because the definition of what it means for two sectors to be adjacent is slightly different. And then we compute an R over S division of the sector graph. So for example, here we have two regions, one corresponding to green and red, and one corresponding to red and purple. So those are the two regions that we got. And then we accordingly define division of the input graph. So now I will show how to do it on this example. So for example, consider this vertex. So this vertex lies in this sector, sector on the left. That's the same sector as this one. Well, that has a corresponding vertex here in the sector graph, and this vertex lies in this region, the region corresponding to green and red vertices that are green and red in this drawing. So that means that we take this vertex and we put it into a region which corresponds to green and red, exactly as it is in this picture. So now I will analyze this, and I will also slightly more formally state what the algorithm is exactly. So the idea of this algorithm was that first we partitioned the plane into the sectors, and then for a sector, so if we have a vertex that lies in some sector, then this sector will determine which regions the vertex V belongs to. So essentially that means that for each sector, we will remember some set of assigned regions, and whenever we get a vertex, then we can just check which sector it lies in. So we figure out one of the sectors that it lies in that sector. And then for that sector, we look at the assigned regions that are assigned to that sector, and these will be the regions that V belongs to. Okay, so I will need the following properties for the sectors. So the first one is that each sector contains at most vertices. Second is that each sector has non-empty intersection with at most S edges. And lastly, we want that there aren't too many sectors, namely n log n over S. But this is fortunately known that one can compute this, and that one can compute this using the algorithm from the previous slide. So Clarkson and Shorter in the late 80s have shown a result which essentially says that the trapezoid decomposition of the sampled edges and vertices will satisfy these properties. So actually they show something very slightly different. because they care about a set of lines in the plane, and they don't have any vertices, but one can use their result in a straightforward way to prove that the trapezoid decomposition of the sampled adjacent vertices will satisfy these properties. And this is, by the way, something that has been used in the design of geometric algorithms. So that is the context that they have studied this in. But we will use it for our graph algorithms. Okay, so now consider, assume that these three conditions are satisfied. So now, what was the algorithm? Well, first we defined or not first, but after we had these sectors, we first defined the sector graph where we had a vertex for each sector, and we put edges between adjacent sectors, or their corresponding vertices, for a certain definition of being adjacent. And as I said, there is some very subtle point here, which is important, but not for the intuition, and I will just skip that. Then we found an R over S division of the sector graph H. And then we defined a division of the graph G. Now, we actually, in a way, we just define it. We do not explicitly compute it, as that would take linear time, which we do not want to spend. We want the whole thing to run in sublinear time, but we define the R division, and then we will be able to, for a query of a vertex, we will be able to answer this the query by an oracle based on this definition. And so essentially what I said is that there is one-to-one correspondence between regions in H and regions in the input graph G. So when you have a region in H, well, these are some vertices in the sector graph, and each of these vertices, they correspond to a sector. So we take all the sectors in the plane that correspond to the vertices of the region, and so we have these sectors in the plane, and now there are some vertices from the original graph that lie in this part of the plane, in the union of these sectors, and those will be exactly the vertices that we put into the corresponding region, into the region that corresponds to this region in RH. So this is how we define the division of G. So now to analyze this, well, first thing that we wanted to prove is that the regions of RG have size at most R. Well, how do we show this? Well, by definition of an R over S division, the regions of RH have size at most R over S. And each region in RG, it corresponds to, it therefore corresponds to vertices that lie in at most R over S different sectors, and each of those sectors has at most S vertices. So that means that together, multiplying those two numbers together, we have that each region has size at most R. Okay, so the second thing that we want to prove is that the boundary, including both the vertices that are shared with other regions and edges that go to other regions, that this boundary has size at most square root of SR. Why is that the case? Well, whenever you have a boundary vertex, then it actually has to lie in a boundary sector. That is by the definition of RG. And moreover, each region in RH has square root R over S boundary sectors, and each of those sectors in turn has at most S vertices. So that means that there are at most square root of SR vertices that are boundary vertices for the region. And the same, or like very similar argument applies to edges. So the edges that leave the region, well, they have to intersect the boundary sectors. Well, at least one boundary sector. And again, there are at most this many boundary sectors. And the second property is that there are at most S edges intersecting any sector. And again, this gives us that the number of the boundary edges for the region is at most square root s times r. Sorry, so I forgot to say this, but I'm ignoring the constants here. All these amounts, they are in a big O, and just to simplify the notation, I removed all the O's from this slide because there were a ton of them. And then lastly, well, there are this many sectors, so that means this many vertices, in the sector graph, and then by the definition of R division, so recall that the definition of the divisions, it said that there aren't too many regions, namely it's the number of vertices divided by the size of the region, that was the allowed number of regions. And if you compute that here, you will get that there are only n log n over R regions, exactly as we desired. Okay, so this is the end of proof of the theorem 2 from a few slides ago. So we have now shown that we can compute this weak R division in sublinear time. So now I will go to MPC algorithms. So first, let me briefly introduce the setting. So it is massively parallel computation. So it means that we have multiple computers with limited memory, and they are all together, they are all performing some computation, and they are doing this in synchronous rounds. And then at the end of the round, each machine sends messages to other machines. It can decide what message to send to each other machine. And then in the next round, each machine receives the messages from the other machines. It does some computation, and then it again sends messages, and it repeats. And we want to minimize the number of rounds. At least in the theoretical community, this is the parameter that has been of the greatest interest. And in this paper, we assume that we have unlimited computation power, so we can do any computation that we want. And also we assume that communication is only limited by the amount of memory. So essentially that means that, well, the messages, they have to be stored in memory to be sent, or to be, but also to be received. That is how the model is formally defined. And that limits how many messages and how big the messages can be that you send. Of course, it is also of interest to realize those two assumptions. And we will pose this as an open problem later on in this presentation. We specifically consider a sublinear space regime where per machine, the memory per machine is n to the delta for some delta strictly smaller than 1. So this is actually useful in practice, because what it means is that it allows you to divide the original problem into smaller subproblems, and then it allows you to do better balancing, a bit better load balancing. So actually, this is also used in practice. And I forgot to say that this whole model, it is inspired by and basically based upon the MapReduce framework, which has been developed by Google. So the whole thing is also of practical interest. At the beginning of the computation, edges are stored arbitrarily on the machines, right? So because we have sublinear space, so the whole input does not fit onto one machine. So I'm just saying that the input is distributed on the machines in some arbitrary way. So in the rest of this presentation, I will be focusing on counting connected components. So just to remind you, we are still assuming that we have straight line embedding available to us. And the algorithm that we show in our paper needs n to the 2/3 plus epsilon space per machine and constant number of rounds. And as I said, you need log n rounds in this space under the 1 versus 2 cycles conjecture if you do not have the embeddings, right? So that means that basically our result is better than this lower bound, but there is no contradiction because we use the embeddings, which the lower bound assumes that you may not use. Okay, and now I will show you a simple algorithm that instead of 2/3 can do 3/4. Essentially, the same ideas that I will show you leads to the n to the 2/3 algorithm, but you just have to apply those ideas in a recursive way, which leads to a more complicated algorithm. So I will not show that. I will only show this simplified algorithm. So now I will say what the algorithm is. So we start by computing weak R division such that each region is stored on a single machine, and we will do it using these parameters. So how do we do this? Well, we will use the algorithm that we have shown on the previous slides. So if you recall, what the algorithm needed as its input was only some sample of edges and vertices. That was the only thing that that was the only way that the algorithm queried the input. So that means that how we start in the MPC model is that we sample some edges and vertices in a distributed way. And then we send all these edges and vertices to one machine. Recall that we have entered a 3/4 memory. And so if we sample this many edges and vertices, then it will fit onto one machine. So that's good. Then locally, we compute an R division oracle using the exact algorithm that I have shown you just a few slides ago. And so this oracle, how is it represented? Well, this oracle can be represented just by giving the trapezoid decomposition, and for each sector in the trapezoid decomposition, you say which regions are assigned to that sector. So that is how we represent the oracle. Well, that means that the size of the oracle is actually, well, what one can show that the size of the oracle is linear in the sample number of edges and vertices. So the oracle still fits onto one machine. And that is good because that allows us to send the oracle to all the other machines. It actually needs slightly more than n to the 3/4 space. I will not say why. It's just because of some technicality how the MPC model is defined exactly. It's not very important for us. But if you were wondering why we need the epsilon here, then this is exactly the reason. Anyway, so now the oracle is stored onto all machines, and that means that any machine can go, and for each of its edges, it can figure out which region the edge, it can figure out which region the edge lies in. And that allows us to then take the edge and send it to the appropriate machine. So we will somehow create some mapping between the regions and the machines. We distribute this mapping to all the computers and to all the machines. And then for each machine, for each of its edges, it knows which machine that edge belongs to, and it just sends it there. And after that, we get exactly what we wanted. We have a weak R division, such that each region is stored on a single machine for these two parameters. Okay, what next? Well, we will somehow locally want to compress each region. And we want to do this separately for each region. And that is very important, that the computation is separate for each region. Because now each region is stored on a single machine. That means that, that the machine can do any computation on the region that it wants to, because this computation is done locally. And that requires that the computation is done separately for each regions, that the computation between different regions does not depend on each other. So what we do is that for each connected component, I mean within that region, we connect its boundary vertices by a path. So for example, you have this, and you remove the connected components that have some intersection, you replace the connected components that have some intersection with the boundary vertices, the set of boundary vertices, and you replace it by a path. And what I would ideally want to say is that if you do this separately to each region and then take union of those modified regions, then the number of connected components will be exactly the same. Well, that's obviously not the case. So for example, here we had this connected component and it just disappeared. But we can deal with this very easily. We just note that this is the case, that we removed one connected component. And one can quite easily show that, that if you ignore these removed connected components, then the rest of the graph will have the same number of connected components after each connected component in each region separately has been replaced by a path. So now the nice thing is that the resulting graph will be much nicer, because for each in each region we replace the region by some other graph which has size proportional to the boundary size of that region. So the total size, if you take union over all these graphs that we computed, so for each region we computed some graph, and you take union over all regions. So the size of the graph is just number of regions times the boundary size of each region. And if you compute that, then you get into the 3/4, which is very nice, because that means that this graph actually will fit onto one machine. So what you do is that you just take all these graphs that you computed for each region, you send them to one machine. So all the compressed representation, you move to one machine. And then on that machine, you count the connected components locally in this graph, in the union of these compressed representations. And of course, you must not forget to add all the counters that account for the connected components that have been removed during the compression phase. And so this is the whole algorithm, and you can verify that each step is very easily done in like each of the sort of steps that I described on the slide. They can be done in a constant number of rounds, and there's only a constant number of them. So you have the total number of rounds will be constant, and the space complexity is n to the 3/4 plus epsilon. Okay, so that was it for this algorithm. And now I will say something about open problems in this sort of direction. So we are almost the first paper that considered embeddings to be part of the input. So this has been done previously, but only for non-planar graphs. Because when you have a graph which is not planar, then but maybe it doesn't have too many crossings, then it's actually hard to find such embedding. And then even in the classical superlinear time setting, it makes sense to assume that you have the embedding as part of your input. But this has never been considered for planar graphs. And I think this new consideration, I think it opens many different possibilities, and there are many possible directions. So, and I will try to go over some of those. So let me say the conjecture. So my conjecture is there's still some low-hanging fruit here, and there's a lot of work to be done. And also, I think that these problems that I will be talking about are very suitable for students. First, I think some of them will not be too hard, so that they will be manageable, the problems. But also, it is very easy to catch up with the literature, because our paper is the first one to consider this class of problems. So in the rest of this talk, I will share with you the problems that I'm the most excited about. So the first problem is, what about other settings? So do embeddings, if we add the assumption of having the embedding of a planar graph, does it give us something in other settings than the ones that we examined in our paper? So what about streaming? What about LCA or local model or the congest model? I don't know. I suspect that for streaming, one could do something interesting. I don't know about the other models, but I think it's still very interesting. Second problem, what about minimum ST cut in MPC? So this is the problem that we have not managed to solve. Maybe one could somehow use duality of the minimum cut, but we don't know how to do it practically to get an algorithm. So I think this is a very exciting problem to look at. And of course, this is still under the assumption that you have the embedding available. So actually, if you do not have the embedding available, then the problem is impossible, again, under the one versus two cycles conjecture. So third problem, can you do some better approximation factor for shortest paths? So in our paper, we did constant factor approximation for shortest paths in this space and round complexity. Can you do something which is much better in the approximation factor, namely 1 plus gamma approximation factor, but and perhaps with slightly worse space complexity. So instead of 2/3, say, have something bigger. But still, I think it would be very interesting if this could be done. So one could say that maybe one could use one of the distance oracles. So we are using in our algorithm, we are using distance oracles, we are using the general ones. And maybe one could somehow use the ones that are designed specifically for planar graphs. However, because of the way that we are using the oracles, this cannot be done in a straightforward way. So I think maybe if one somehow thought about how exactly the oracles, the distance oracles work in planar graphs, and applied some of those techniques to our algorithm, then maybe it would be possible to get a better approximation factor for shortest paths. And a fourth problem is that is the question whether it's possible to get MPC algorithms with space better than 2/3 plus epsilon. So this is interesting in that in the MPC world, usually when you can get below 1, so you can get n to the 0.99, then usually you can get arbitrarily close to 0. You can do just n to the epsilon for any epsilon strictly greater than 0. And the reason is, like the intuitive reason is that usually when you have the algorithm, what it allows you to do is that you can take the original input and you reduce the size of the input to something that is sublinear. And then if you take this algorithm and you just repeat, you recurse, then this will actually lead to n to the epsilon algorithm. However, this is not the case for our setting, because yes, we are able to take the input and reduce its size, and reduce the size of the input of the problem. But the issue here is that while reducing the size of the input, we lose the embedding, and then we cannot recurse. So that is the issue why we cannot easily get to anything better than n to the 2/3. So sixth problem is property testing with respect to Hamming distance. So something that I haven't told you about in this talk is that we also did some property testing, but we did it with respect to some quite non-standard distance, or well, at least it is non-standard for property testing. And the reason why we use this distance is simply that that's the distance that our techniques sort of naturally leads to. But the question is something possible for the standard Hamming distance? So that is the distance that is usually used in property testing. Can we do something clever under the Hamming distance? And seventh, and the last problem that I want to mention is considering time complexity of the MPC algorithms. So as I said, in our paper, we have completely ignored the time complexity of the MPC algorithms. they are all polynomial, but maybe one could get to something like near linear. But we have not tried. So the question is whether something clever can be done to improve the time complexity here. Obviously, one can analyze the complexity of our algorithms. I think there could be even some simpler, so some like straightforward optimizations, but perhaps this deserves to be looked into more. And I think it is possible that one could come up with something more clever to improve the complexity of the algorithms. Specifically, I think for the approximate shortest path, I think this would be very interesting. And there, I think it could be possible to do something nice. Okay, so in summary, in our paper, we give new results for various problems, and they are all under the assumption that we have a nice embedding available to us. So in this talk, I was talking about straight line embeddings, but as I said at the beginning, we also consider some other embeddings, and they don't even have to be planar. All the results in our paper, they depend on a sublinear-time algorithm for computing an oracle, which can answer queries about weak R division. And this is the algorithm that I've shown you in this presentation. And there are many, many unexplored directions that I'm hoping that maybe somebody will look at. And yeah, if you have any questions, then feel free to email me. If you have any ideas about the problems that I mentioned, then also, or even if you have some other problems that you find interesting and you want to share them with me, then definitely do send me an email. Okay, that's it from me, and have a nice day.